This is stochastic processes, Model 7, Brownian motion and its applications. This is lecture 6, some important stochastic differential equations and their solutions. In the last 5 lectures, we have discussed Brownian motion and its properties, then a process derived from the Brownian motion. Then we have discussed a stochastic differential equation that is related to the Brownian motion only. Then we have discussed the Ito integral, that's the integration with respect to the Brownian motion. Then we discussed the Ito formula, that is the one we can use to solve some special cases of stochastic differential equations. At the end, as a lecture 6, we are going to discuss some important stochastic differential equations with their solutions. And these stochastic differential equations arises in the application of mathematical finance. In this lecture, we are going to discuss 4 different stochastic differential equations. All are related to the applications of financial mathematics. The first one is geometric Brownian motion, and that's a stochastic process. This stochastic differential equation, the corresponding stochastic differential equation is called a Black-Scholes model. The second model is Ornstein-Uhlenbeck process. The third and fourth are the interest rate models. So these 4 models we are going to discuss in this lecture in detail. The first model, this is nothing but Black-Scholes model. Let ST be the stock price at time t and mu be the constant growth rate of a stock and sigma be the volatility. Consider the stochastic differential equation, that is dSt is equal to mu times St dt plus sigma times St dWt at 0 you know the value, that is S0. So here we made the assumption sigma is the volatility, which is a constant, but in the real world scenario the volatility is not a constant, but for this particular Black-Scholes model we have chosen volatility is a constant. In general, volatility is a random variable, therefore over the time that is a stochastic process also. So it's a stochastic volatility. The corresponding model is a stochastic volatility model. But here the volatility we treated as a constant, therefore it's a sigma times S of t, not a function of t. And the growth rate, that is mu, that's also a constant. So the mu can take the value from minus infinity to infinity, whereas sigma is the volatility, so it is greater than 0. Both are constant. So the corresponding stochastic differential equation, that is the increment of S, is mu times S of t dt plus sigma times S of t dWt. So because of this Wt, dWt, this equation is a stochastic differential equation. We are going to find out the solution of this stochastic differential equation, and the solution is a stochastic process, that is nothing but the geometric Brownian motion, and the corresponding this model is called a Black-Scholes model. Assume that the solution S of t is a function of t, Wt. Now we can use the Ito formula version 2, that is nothing but dSt is equal to partial derivative with respect to t dt, partial derivative with respect to x dWt, and half times a partial derivative with respect to second derivative with respect to x dt. Therefore, you will have two terms with integration dt and one term with the factor dwt. So now you can compare this with the given stochastic differential equation. So this is the given stochastic differential equation, d of st is equal to this one, whereas by the Ito formula the d of st is written this one. So you can compare this equation with the given stochastic differential equation. So you will get f, the partial derivative with respect to x, that is nothing but the coefficient of dwt, that is sigma times s of t, that is sigma times f. Here the coefficient of dt is ft plus of second derivative with respect to x. So therefore ft plus of times f double derivative with respect to x, that is mu times f, mu times st, that is mu times f. So you can solve this equation fx equal to sigma times f. By solving you will get f is equal to e power sigma times x some function of t, because this is a derivative with respect to x, partial derivative with respect to x. Therefore the function is e power sigma times x some function of t. You can take a second partial derivative with respect to x, therefore you will get a f xx will be sigma square f, and here you can take a partial derivative with respect to t, therefore you will get k dash of t e power sigma x. So you can substitute a f t here and f double x here, therefore you will get a k dash of t e power sigma x is same as mu times f minus of sigma square f. Therefore substituting ft and fxx in this equation, you will get a k dash of t e power sigma x is equal to mu minus sigma square by 2 f. Still k of t is unknown, so you have to find out the k of t, then you can get the f. So substitute f is equal to e power sigma x k of t, therefore you will have a equation, the ODE for the equation with the k of t. Therefore you can solve that equation and get the k of t. So k of t is nothing but s naught, that is s at a point s initially at 0, e power mu minus sigma square t. So you substitute this in the here, therefore your f of t comma wt is e power sigma times wt s naught e power mu minus sigma square t. Therefore s of t will be s naught e power mu minus sigma square t plus sigma times wt. Substituting k of t in this equation, f is equal to say e power sigma x k t, where x is nothing but the wt. Therefore your solution is s naught e power mu minus sigma square by 2 times t plus of wt. So this is a solution of a given stochastic differential equation. This we got by using the Ito formula. By using the Ito formula version 2, without solving the stochastic differential equation, by using a Ito formula we are finding the solution of given stochastic differential equation. One can prove that s of t is a log normal distribution, because wt is a normal distribution with the mean 0 and the variance t, and this is of the form e power mu minus sigma square t plus sigma times wt. Therefore the s of t will be log normal distribution, and also you can find out mean and variance. So the mean will be expectation of s naught e power mu t. Similarly you can find out the expectation of s of t whole square Using these two, you can find out the variance of S of t also. So for this Black-Scholes model, we are finding the solution of S of t. Also we are finding the distribution of S of t, that is a log normal distribution, and we know the mean and variance in terms of mu and sigma square. We can also discuss what is the asymptotic behavior of the solution. Because the solution is e power mu minus sigma square by 2 multiplied by t plus sigma times wt, as a t tends to infinity, what happens? So if mu is greater than sigma square by 2, if mu is greater than sigma square by 2, as a t tends to infinity, S of t will tends to infinity. If mu is less than sigma square by 2, then as a t tends to infinity, S of t tends to 0, because the whole term is in the e power exponential of power. If mu is equal to sigma square by 2, as a t tends to infinity, St will fluctuate between arbitrary large and arbitrary small value. Note that mu is a constant growth rate of the stock and sigma is a volatility. So as a t tends to infinity, if based on these three conditions, accordingly St tends to infinity or St tends to 0 or St will be fluctuating as a t tends to infinity. This has the application in finance. Consider European call option return on t equal to 0 with the maturity t equal to capital T and the strike price capital K. So you can choose the mu is nothing but the interest rate with the notation R, and the volatility is a sigma, that is a constant, and St be the stock price. Therefore St, the solution S of 0 e power, I replaced mu by R, therefore R is the interest rate here. So R minus half sigma square t plus sigma times Wt be the geometric Brownian motion with the mean rate of return R, where the initial stock price is S of 0 is positive and Wt is a Brownian motion. So it has a direct application in the finance. Suppose you choose a positive constant, which is a strike price at the maturity date capital T. Value of the option at time t, at time capital T, is S of capital T minus K superscript plus, where x superscript plus means maximum of x comma 0. Then one can show that for t greater than 0, the expectation of e power minus r times capital T, the random variable is S of capital T minus K power superscript plus, that means it is a maximum of x comma 0 for x superscript plus, that means it will return the value 0 or whatever the x for the maximum. So that is nothing but S of 0 psi of d suffix plus t comma S of 0 minus k times e power minus r of capital T psi of d minus t comma S of 0, where t plus and t minus are defined in this form, and psi is the cumulative standard normal distribution function. Psi of y is defined. What is the probability between minus infinity to till y in the standard normal distributed random variable? So either minus infinity to y or minus y to infinity, because of it is symmetric. So this expectation, this is a discounted one, e power minus RT. So the expected return will be calculated using the CDF of standard normal distribution, and we should know the strike price value capital K and the maturity date capital T, and also the interest rate R, and the volatility sigma square also, sigma also. Now we are moving into the second model, that is a Ornstein-Uhlenbeck process. Consider the stochastic differential equation dxt is equal to minus mu times xt dt plus sigma times dwt, where mu and sigma are constants. And this equation is also referred as a Langevin equation. This equation is useful to model the velocity at time t of a free particle that performs a Brownian motion. If you discretize with the dt is equal to 1, then you will get the increment is nothing but x of t plus 1 minus x of t, that is dt is equal to 1. Therefore, this increment is w of t plus 1 minus w of t. Therefore, if you label mu dash t is equal to 1 plus mu, then you can transform the equation in the discretized version. So, this time series model can be considered as a discrete analog at the solution of the same equation 1. So, you can develop the time series model by discretizing the above stochastic differential equation also. And the stochastic differential equation can be interpreted with the integral equation also, because it is dxt is equal to minus mu times xt dt plus sigma times dwt. Therefore, you can write down this as the xt is equal to x at 0 plus sigma times wt minus mu times integration 0 to t x of s ds. X of t is unknown, therefore this is a integral equation. It is very difficult to get the solution, but here we are using the Ito formula, which is easy to get the solution. Assume that the solution is of the form e power mu t x. So, use the version 2 of Ito formula. That means you have to find out first derivative with respect to t, first derivative with respect to x, second derivative with respect to x. Find out those things, then substitute in the equation, then you can get the solution of x of t, that is x of t is equal to e power minus mu t x of 0 plus sigma times the integration 0 to t e power minus mu t minus s dws. Note that this is a Ito integral, because this is a integration with respect to ws, but the integrand is a non-random function of time. Therefore, it is easy to get the solution. We have already discussed as an example how to solve the Ito integral with the integrand is a non-random function. So, you can refer that example and you can get the solution. And this is a strong solution, immaterial of the path of Brownian motion, the solution for the equation 1. You know that this is whenever the integrand is a non-random function, the Ito integral with the deterministic integrand is normally distributed with the mean 0 and the variance in terms of integration. So, you can conclude when x of t is a constant or x of 0 is a normally distributed random variable, you can conclude x of t is also normal distributed random variable. if x of 0 is a constant, or if x of 0 is normal distributed random variable, then x of t one can prove that is also normal distributed random variable. So we have to use the eta integral of non-random function of time. So you can find, if x of 0 is equal to 0, you can find the mean of x of t, mean of x of t. So this will be 0, and this is normal distributed random variable with the mean 0. Therefore, a mean of xt will be 0. And the variance also one can find. Before that, you should find out the expectation of xt whole square. Then using the formula of variance of xt is equal to expectation of xt whole square minus expectation of t whole square, you can find out the variance of xt. And also you can find out the covariance between the two random variables x of t and x of s. Also we can prove this, the solution xt is a Markov process with the Gaussian transition probability density is in this form. In the stable case, as a t tends to infinity, you can make out sigma square t is nothing but some theta. Then you can find out the limiting distribution, the transition probability density, that is a standard normal distribution. That is a normal distribution with the mean 0 and the variance sigma, variance theta. So we can prove the xt is a Markov process with the Gaussian transition probability density, as well as a t tends to infinity, we can prove the transition probability. So this is a normal distributed random variable with the mean 0 and the variance theta. Now we are moving into the third important stochastic differential equation. This is the one of the oldest and commonly used interest rate model, Vasicek interest rate model. It is used to model a short rate, that is the instantaneous rate, that is the rate model is valid for a short period. So suppose capital R of t, that is a short rate stochastic process at time t, then this model assumes the following stochastic differential equation, that is a d RT is equal to alpha minus beta times R of t multiplied by dt plus sigma dwt, where the alpha greater than 0, beta greater than 0, sigma greater than 0. Sigma is the order of magnitude of the fluctuation of R of t around alpha. Sigma is the volatility. So we are going to find the solution of this stochastic differential equation. Assume that Lipschitz condition is satisfied. So here we are not going to use Ito's formula, but we are going to use the increment concept. So increment of e power beta t RT will have two terms, then substitute d of RT from the stochastic differential equation. The previous is stochastic differential equation. You substitute d RT from here in this place. So it is e power bt, dRT is replaced by the given stochastic differential equation, so that is nothing but this one, plus beta times e power beta t RT dt. So that is nothing but some terms will be cancelled out, so you will get e power beta t RT is nothing but, because this is a differential form, so we are making an integral form. Therefore, e power beta t RT will be R of 0 alpha times integration 0 to t e power beta s ds. So, this is the Riemann integral. Sigma times integration 0 to t e power beta s dws. This is a Riemann, this is a Ito integral, but the integrand is a non-random function of time. Therefore, this is a strong solution for a given stochastic differential equation. Therefore, the R of t will be R of 0 e power minus beta t plus this term and the last term. So, this is a Ito integral, but the integrand is the non-random function. And you know that Ito integral with the non-random function of time as an integrand, that will be a normal distributed random variable. Therefore, you can find out the distribution of R of t also. So, if R of 0 is constant, then you can find out the distribution of R of t, which is a Gaussian or normal distributed random variable with the mean and variance is given in this form. One can find out the mean and variance from this solution term by term. You can find out, and we can find out the mean of R of t. Similarly, you can find the variance of R of t, and we can discuss as a t tends to infinity what is the distribution of R of t also. So, when R of t is much greater than alpha by beta, then the process will bring down back to alpha by beta, and if R of t is very smaller comparing with alpha by beta, then also the process will bring it up to the alpha by beta. That means this model is known as a mean reverting OU process. Because of this property, if R of t is much higher than alpha by beta, the process brings it down back to the alpha by beta. If R of t is much lower than alpha by beta, then also the process will bring it up to the alpha by beta. Therefore, it's called a mean reverting OU process. If R of t is equal to alpha by beta, then the drift is 0. If R of t is less than alpha by beta, then the drift is greater than 0, implies the process will try to pull back. If R of t is greater than alpha by beta, then the drift is less than 0, implies the process will try to pull down. So, these are all the behavior based on R of t is with the alpha by beta. Hence, interest rate does not go too high or too low. So, this is applicable from an economic viewpoint also. The only drawback of this model is that it assumes negative values with the positive probability, which is undesirable property. The Vasicek interest rate model is a mean reverting OU process, but the drawback is it takes a negative value with the positive probability, which is undesirable property. Now we are moving into the CIR model. This is also the interest rate model, and this also has application in financial mathematics. So, the underlying stochastic differential equation is dRT is equal to alpha minus beta times RT dt plus sigma square root of RT dWt. We cannot use the Ito formula to solve the stochastic differential equation, but we are finding the solution through the increments. In this model, the volatility also depends on the interest rate. Earlier, the volatility, here it is a sigma, but here it is a sigma times the square root of RT. So, the volatility also depends on the interest rate, unlike a Vasicek interest rate model, where it was constant. And this model is also mean reverting model because of this one, alpha minus beta times RT dt. Therefore, this model is also called a mean reverting model. As soon as RT tends to 0, the model becomes a dRT is equal to alpha times dt. This implies R of t, if you solve this equation, you will get R of t is equal to R of 0 plus alpha t. That means this process will make sure that R of t linearly increases as R of 0 greater than 0 and alpha times t is greater than 0. So, this is observation as RT tends to 0. Now, we are discussing the solution. This model does not have a closed form solution, only the numerical schemes can be used to solve the CAR model. So, we are finding what is the expectation of R of t. So, we cannot use the Ito formula to get the solution, only numerical schemes can be used to solve the CAR model. Now, we are finding the expectation of R of t. For that, we are taking an increment of e power beta t RT, get the terms, then substitute d of RT from the previous equation. Therefore, you will get e power by converting into the by converting into integral equation, you will get e power beta t Bt RT is equal to R of 0 integration beta times e power beta s Rs ds. Substitute, you can get the mean of we know that so basically we should find the mean and variance of the Ito integral 0 to t sigma times square root of R of s dws. Since this is a Ito integral and that is also a martingale, since the expectation will be 0, because this integration, if you make it as I of t, since it is a martingale, the expectation of I of t is same as expectation of I of 0, and the expectation of I of 0 is 0. Therefore, the expectation of I of t will be 0. Therefore, from the previous equation, expectation of RT will be R of 0 e power minus beta t, this term multiplied by e power minus beta t, this whole Ito integral multiplied by e power minus beta t, and since this expectation is 0, therefore, expectation of R of t with the multiplication e power beta t will be R of 0 plus alpha by beta e power beta t minus 1. Therefore, expectation of R of t will be, you multiply this side with the e power minus beta t. Similarly, one can find out the variance of R of t, but for that we have to find out expectation of R of t whole square. So, for that you have to find out the increment and so on, second increment, then find out the expectation of R of t whole square, then you can find out the variance of R of t. So, in this CAR model, you are not giving the closed form solution because the Ito formula does not work. Whereas we are finding the mean and variance of R of t using the mean and variance of Ito integral. Now we are discussing as a t tends to infinity, what happens. As a t tends to infinity, from this equation you can make out this is expectation of R of t. So, as a t tends to infinity, you will get with the assumption r of 0 is equal to 0. So expectation of r of t is equal to alpha by beta. As a t tends to infinity with r of 0 is equal to 0, expectation of t will be alpha by beta. Similarly, you can find out the variance of r of t, that is as a t tends to infinity, you will get this term, and r of 0 is equal to 0, therefore you will get alpha times sigma square by 2 beta square. So this is a asymptotic behavior of r of t with the assumption r of 0 is equal to 0. If you choose alpha and beta appropriately, we can bring down variance, because the variance is in a longer run, the variance is in terms of alpha and beta. So we can bring down the variance and hence bringing more stability to the model. You can make the model stable by properly choosing alpha and beta. This CAR model has a lot of application, in particular the bond pricing models. So using CAR model, the bond pricing equation can be solved explicitly. With this, we have completed 6 lectures in Brownian motion and its application, starting with the Brownian motion definition and the properties, then process derived from the Brownian motion. In particular, we have discussed geometric Brownian motion, Levy processes, and in the third lecture we have discussed the stochastic differential equation. In the fourth lecture we have discussed Ito integral and a few properties of Ito integral, and we have discussed a few examples also in the Ito integrals. The fourth lecture we have discussed in the fourth lecture we have discussed the Ito integral, and the fifth lecture we have discussed the Ito formula that is useful to solve some special cases of stochastic differential equation. And in the last lecture we have discussed some important stochastic differential equation and their solutions. Here the important means these stochastic differential equations are having applications in mathematical finance. The first model is a Black-Scholes model we have discussed. The second model is a OU process, and the third and fourth one are the models for the interest rate. Some stochastic differential equation we solved using a Ito formula, and in one model we have not given the closed form solution, which does not exist in that case, and we have discussed the mean and variance and asymptotic behavior. With this, the Module 7 Brownian motion and its application is completed.